Hello, everyone. So I will start from the 4 to 5, the first part with my network, the FHE AI session. So I will start from a very brief introduction of myself. I did my PhD in cybersecurity. So very related to what you have already heard about privacy preserving data access and data sharing, include the differential privacy, filter learning, fully homomorphic encryption, so all of the schemes you have heard before. So if you have any question about the PhD experience, also the cryptography schemes, you can come to me. We can have a discussion, or you can have any question of my experience. And now I'm head of R&D, the research department in the My Network. I have been doing this for 1.5 years. Also, this year I was in the Ethereum Foundation Fellowship. So also anyone who is interested with Ethereum Foundation Fellowship, we can have a discussion or any question on that. So I will start from the technical part, and our BD Christian, he will manage to the second part with more economic things. So my network is actually a FHE restaking layer for AI networks, and we will use fully homomorphic encryption scheme to do the revolution of POS validation. So the story actually begins with a presentation by Vitalik in 2024 in the Web3 Festival in Hong Kong. And he mentioned that voting is actually a very important use case. So we have the schemes and we have the solutions with the CK snarks. But if we want to get the really best properties, then MPC and FHE are what we really have to use. This is very straightforward and easy to understand, because as we already know that FHE provide end-to-end encryption, Zama highlight is HTTPZ. So we have in the area of HTTPZ, and FHE can exactly provide the fully encrypted from the beginning to end. So that's why it has the best security properties. And this is what exactly a FHE restaking layer for AI and POS network. Later, Christian will go for more details with all the layers and from a more economic aspect. But for me, I will directly go to our technique and what's the problem, what's the problem we are solving, and what's our solution. So actually, there is a use case or a question. Let's think about. I think most of us know BitTensor. It's an AI network, and in that validation and in their miner and the validation process, there is the challenge and the response process. So validators has to validate the result of the miners is accurate or not. So, however, in this process, in this kind of validation network, there is one big problem in that how to prevent the free riding of the validators, because the validator basically can copy the values from others and pretend it's their work, but actually they didn't do any effort on that. So this is our first idea. Also, we published a paper on that. So the consensus is also actually called the proof of intelligence, which is expectedly for AI networks. And we will use FHE to protect and provide a consensus security. So this POI with FHE framework is first introduced the POI consensus mechanism utilizing FHE. This approach safeguards the outcomes of machine learning tasks by ensuring fair voting and secure reward distribution among validators, which provide a robust framework for secure and transparent execution of actions within the network. So this is a main contribution. And also, it prevents the malicious validators. With FHE encryption, the result of AI tasks from participants are encrypted, and which preventing the malicious validator from free riding. And third part is computational security. And I think from a technical point, also academic point, it's very important to us to analyze these security properties that can bring from FHE. And for our computation security, that this framework provides the path to ensure fair and secure consensus with end-to-end encryption, which is especially crucial to data-intensive works like AI or deep network. And the consensus is reached, and the ciphertext and the computation is fully decentralized. So there are the main advantages of our framework. And there are the security properties. I think if you are in academic, you definitely know it and might very familiar with it. So we have indistinguishability of the CPA security, which means that actually you cannot distinguish two ciphertexts belongs to which plaintext. So by giving two plaintexts after encryption, you cannot say which exactly the corresponding plaintext. So this is a formula of it. And the second one is the correctness. We know that fully homomorphic encryption is actually add noises. So we have the bootstrapping to prevent the noisy overlapping. But the question is that once we introduce the noise, then how we can ensure that the encryption and also the decryption can be done correctly. So there are actually some security properties which we can already define with fully homomorphic encryption. And also our POI mechanism with under fully homomorphic encryption can help with it, can preserve it. So there is the security properties like we defined in the beginning. And then this is our framework. So instead of giving the plaintext directly, we have the miner and a validator in most of the AI validation networks. So the miner and the validator, they will have the challenge and the response phases. The miner, based on the machine learning task, AI task, they will generate their results. And the validators have to validate their results with a response. And the writes that the results that they give will be encrypted by the public key of FHE. So all the validators, they will take the public key and encrypt it with their results with the public key. And we call it a score, actually. And then it generates the ciphertext. So instead of transmitting the plaintext directly, we will have the ciphertext. And this ciphertext will be sent to the consensus layer to reach the FHE computation under the ciphertext. And later we will see exactly the concept and the calculation behind it. So the encrypted consensus will be reached, and then we will use multi-party computation shareholder FHE to do the decryption. The reason is that we don't want a single identity to have the single key, secret key to decrypt it. So we will distribute all the keys into multi-party, and each party, they will have a piece of it. And then in the end, once it decrypts all like the ciphertext pieces, we will have the plaintext consensus. So this is an overview of the encrypted POI consensus with FHE. And we have defined the security behaviors of the stakeholder. So for the stakeholder, we basically have the encryptor, have the third party, have the decryptor. So we have for the encryptor, they will have the PK and a part of the secret key. For a third party, he will only have the public key. And for the decryptor, because actually the encryptor can be decrypted as well, or we can have separate validators for it. So they will have the same values. And the input-output will be other concept that we will introduce. W is basically the weight, which means the score. So we will use the encryption to encrypt it, and it will generate the ciphertext score, the weight. And the third party will only get the ciphertext weight and generate the ciphertext emission. So the third parties, they will get the ciphertext emission, and we will use the secret key to decrypt the part of the emission. So this is the input-output relationship for the stakeholders. And this is a concept. So we will have the weight. So when miner, the definition of the weight is the following. So the miners, they will submit their result to the validators. And this validator will access this accuracy of these submissions. So actually, this will be, the weight will be a matrix from all the miners and validators. And it will only have the result from 0 to 1, or yes or no. It's based on the machine learning task. If it's like a face recognition, then definitely it has the accuracy, like 19%, 95%, or even 20%. So it will be a value from 0 to 1. So this is what we call the weight. And the weight cannot be leaked because this is a secret from the validators. So we will use the shareholder FHE, the encryption function of the public key to encrypt it. And then we will generate the CW. C means ciphertext. Weight is like the matrix of it. So, and this will be from one validator. And each validator will send this encrypted weight vector to the consensus lead node. And this consensus lead node will combine the vector, use a homomorphic encryption function to generate this matrix. So actually, this is CW is a vector, and the C capital W will be a matrix. And the matrix will be the dimension will be 32 plus I. I is the number of validators. So this is a matrix, and after the matrix, we will calculate the ranking. The ranking calculation is quite easy actually. We will take the ciphertext of the matrix, and we will plus the staking of the validators. And the ranking of this stakeholder will be the ranking of the overall. And as we can see, this ranking is actually ciphertext. And our next step is going to use the partial decryption of the secret key to decrypt this ranking. And to reduce the computation complexity of the emission process, because in the end, we have to calculate the emission, how we can reward these validators, players, but we already can give the result here, because we first decrypt the ranking ciphertext here. And for secure decryption, we will use multi-party computation, FHE decryption. And in this method, each decryption node will have a share of the secret key, which enables them to decrypt and retrieve a part of the plaintext result. And we will combine all this together, which will be the plaintext ranking. So this will be the ranking, and based on the ranking, we will calculate the consensus. So we have to say that if majority of the person who reach the consensus or not. So here we have another parameter T. T is called trust rate. So if we have the trust rate of the sigma, and the sigma is more than a shareholder, then if the shareholder case meet, which means that more than case party, they agrees on this consensus, then we will thinking that this consensus is reached. And the consensus is reached, so we will just calculate the C of the ranking, and this will be emissions to all the validators. So in this case, it's a whole process of the validation process based on the ciphertext without the leakage of the value of the validators. And this is our the product, the first part of how we do proof of intelligence consensus with FHE. And we also have the complexity analysis. As we can see that with fully homomorphic encryption, it actually adds the computation complexity as we add higher security level. And this is the metric addition and the multiplication of a metric with a real number. And as we can see, to be honest, it didn't increase a lot of computation cost because we only encrypt the matrix, and the matrix is size limited. So this is a POI with consensus, and now with Zama, because we are a strategic partner with Zama. So today we focus on one of our use cases with Zama, how to build FHE AI. And Zama, I think it's their core FHE event. So everyone basically knows that Zama is an open source cryptography company, build state-of-art FHE solution for blockchain and AI. And now actually my network is a Zama strategy partner. And so in the picture, it actually shows what Zama has. Zama basically has 3 libraries with TFHE ML and the concrete library, and also the Roost. So based on these 3 libraries, we will work exactly on the concrete library. So with the concrete library, this is how our scheme will look like. So with Zama, we will try to compile directly from the library of the, it's already, this use case or this framework already validated, because we have basically 5 steps and 3 partners. So in the left hand, this is FHE 101, just in case everyone kind of understand the concept. So we will have a value, their plain text in the client side. And we will use the encryption function to encrypt the value. And instead of sending the plain text, we will send the ciphertext to the server. And once the server they get this plain text, they will call the function FHE from concrete directly. So this is already written in the concrete library. We are just build FHE ML based on the concrete library. So in the step 1, we have model developer. And in the model developer, they will have the plain text. X chain plain text, Y chain plain text, and they will get the model, so the neural net classifier. And after the classifier, we will compile the model by FHE model developer. So this is actually all the function you can call from compile. Oh, sorry, from concrete library. And then we will generate 2 outputs, the model client zip and also the model server zip. The model client zip will go to the model side, model customer side, and the model server will go to model's host side. And in the left side, the step 3 is actually, it's a digital recognition with meanings, very obviously. And then this will be the input, because the user will encrypt the value. It will be XZT. And it will conduct this model quantization encryption with serialization. And then this CT will send to the server, to the model hoster. And the model hoster will do the interference with YCT. And they will convert this YCT to the model customer and compare with YCT. It will decrypt it with a plain text, with the secret keys, and it will generate a YPT, so which will be the plain text. And the validators, they just need to vote with a compare with Y or YPT, it's true or false. This exactly will be done by our proof of intelligence consensus that we mentioned before, and we called it a mind-independent validator SDK. And a more detailed picture is actually here. So if you can, we actually include the source code of these all the steps. So as we say that if it's how to train the neural nets, we can directly compile from the concrete. So there are all the exactly functions that we can call from concrete. And after that, it's FHE validation, right? So after we have the FHE machine learning, so inference process, we have the FHE validation. So FHE validation, this is what exactly we will work on. So when FHE AI meet FHE validation, so we will have the model customer, they want to do the digit concatenation, and there is a process that we already explained before. And here, that if data is very incentive, then FHE AI is a must-to-have, because what if we have credit score history, like front records, customer behavior, wallet history, tax reporting. So once we have all this incentive data, then we have to work exactly on AI instead of the single FHE scheme. So here we have attached with FHE AI and FHE validation summary. We can see that we have a lot of opportunities, because this end-to-end protection of model IP use data and predict result. It also provides fair and verifiable validation. It can reduce the node requirements for trustable consensus, and new paradigm is coming. But we have to admit that FHE computation speed needs more optimization accelerations. Also, FHE has a learning curve and it's in short of talent. More awareness and adoption. Also, Zama FHE AI support a limited number of the deep learning models. So how we can cover these questions, it's a challenge. And I think there's one slide that's missing, but it's fine. And for more demos and docs, you can visit our website with community. So if you can visit, you can find our white paper, also how our demo looks like. And this is basically from my technical point. Later, Christian will give more on like community side or like economic side. But do you have any questions so far about techniques or the schemes that we are using right now? Yes?
Sorry, I was late, so maybe you already covered it. What's the maximum upper size, the model size that you have tried?
Sorry?
Yeah, sorry. Can you hear me now?
Yes.
My question is, what's the maximum model size that you have tried? Or what's the upper limit that you can scale this?
It's a very, very nice question because now what's the data set we are using right now is only limited to MNIST. As you know, the MNIST is very, very limited. So in this case, we cannot support large learning models or even complexity neural nets.
Yeah, for them, NIST are using scikit-learn under the hood, or do you support more advanced machine learning frameworks, PyTorch, TensorFlow?
Yes, so that's what we are exactly working on because concrete actually it's very limited. So we want to convert, so we cooperate with Zama, we want to support on the JavaScript instead of on the Rust or on the Python. So with JavaScript, you can provide larger neural net training models on that. So this is our strategy cooperation on that.
Yeah. Last question. What's the performance impact? Is it 2x, 10x, 100x on the raw model?
So this hasn't been calculated or estimated, to be honest, because what we have estimated is basically from a theoretical way, and theoretical ways are far to go when we consider the chips, the accelerations. So now I cannot give exactly the result on that, and I cannot say it's 2 times, 3 times, or sometimes, but you can look forward our experiment in the future.
Yeah, thanks. Maybe last question, what hardware does it need to run? Does it support GPU or does it work only on CPU?
We do not work on the core processor, so also the chips, this is not what we're exactly working on because Mind in somehow still a validation network. So we cooperate on the validation. Also, this is FHE AI with validation. So this, and with chips, I think they have their GPU already working on the concrete with Zama. So this is not exactly our target to focus on.
Yeah, thank you very much.
Thank you. Christian?
Ashley is our head of research. I'm head of BD at My Network and US co-founder. So Ashley talked about our schemes and going from theory to application. I'm going to talk about our efforts going from application to finding product market fit and where we found sweet spots in tech stacks that we can apply FHE. So, oh, the clicker. So it was a good question at the end. So I actually can give a figure because I was just speaking with Optalysis, and they're working on a photonic chip, and the chip companies are working on scaling, obviously, hardware. So they gave me a figure of 1,000x. Right now, I think Kornami is the main chip provider for Zama and others. So there is a hardware acceleration effort. But if you're on a BD team at an FHE project, you don't have the luxury of waiting for the acceleration. So the idea is, where are there areas in tech stacks now where there's already a window of time that some other process is being performed, where you can apply FHE and it doesn't add time to the overall process? And so I'll talk a little bit about 2 products that we shipped where we kind of found this sweet spot, which led us to our ultimate flagship product, which is a lot of what Ashley just spent some time talking about. But the first one was a decentralized data lake. So the pitch is really easy. If you're already storing data in raw format, why not have it encrypted and allow for FHE computation to be performed on top of it so that cold data is protected, lowering the chance of breaches? So we made a data pack and we shipped that to Arweave, IPFS, and Greenfield. Very sexy product, at least to a lot of builders in the space. The problem is that decentralized data storage is still too slow. And most projects in the industry are still using Amazon and Google. So we moved on and we found a real use case with bridges. Now, bridges are one of the most vulnerable areas in Web3. And we know that one area of attack is always that if the nodes operating a bridge can see the intent or see the transaction before it's executed, they run MEV and they can front run trades. And so Chainlink was building a bridge last summer. They were doing a beta test of CCIP. And they were sending assets, basically stable bank coins, into public chains and back again, and everything was going swimmingly. The problem is that the banks are working with regulators, and the regulators were saying, wait a minute, the message that initiates the transaction is not encrypted. That means that the nodes running the bridge can see the transaction. And of course, Chainlink's a very secure company, and they promised that would never happen, but that wasn't enough to appease the regulators. Even SWIFT has an encryption method. So as you send assets from bank to bank and all the intermediaries in between, they receive the data, they decrypt it, they run the processing, they re-encrypt it, they send it on again. And so this was a basic standard of basically confidentiality that Web3 had to be able to achieve. And so we were able to apply an FHE for the messaging layer. So we keep that entire intent layer in an encrypted state, and the computation can be performed without ever decrypting it. This was a huge use case. Solved a big problem, and Chainlink ended up making us tier 1 channel partners for that solution. So this bridge solution is something we can build on any bridge. We'll be working with Phoenix and Inco to do the same thing with Wormhole. If you have FHE from the first block, that's very helpful, but all the assets coming into those L1s and L2s can be tracked and are traceable. So you need to have FHE protection going into those chains as well. But again, what we found with this bridge particularly is that it's more of an enterprise use case. So again, not quite a sweet spot. We really want FHE to scale. We really want a kind of killer use case that grabs market attention, that grabs dev attention and builder attention. And we found that this isn't quite it yet, even though it was really well received by Chainlink and their partners. So what we ended up coming to, like Ashley was talking about, is this private voting case. The really simple explanation is obviously just a DAO. We see DAO influence happening around voting in DAOs by those in a DAO that have a lot of influence, and there are consequences for voting against them. So this has been a problem for years. But you can take this problem into validation. So anywhere where you have a node network that has to come to consensus around anything, if there's enough time for consensus to be achieved, you can run FHE computation. Specifically, a validation use case that we were looking at is within AI. So we were early contributors to BitTensor. We found that validators were ranking models and validating models, and basically whatever validator had the most Tau tokens staked typically also had the most compute resources and were also going to get the right answer, and so everybody copied them. It's called the lazy node problem. And this is a problem with subnet 4, and then we talked to subnet 6, and then 21 and 26, and every single subnet we talked to said this was a major issue that BitTensor did not solve for in their framework. Every subnet had to figure out how to overcome this problem. And it's a substantial problem because if you want decentralized AI to take any meaningful amount of share from centralized AI, the models have to work, they have to be reliable, people have to use them. And so the ranking process is very critical. So private voting has turned out to be, it looks like a flagship product and one that's grabbing a lot of attention. Now there's a lot of different kinds of consensus that have to be achieved in AI networks. This is the most important one. I will just touch on this slide briefly by saying that, again, since we're validating creating a shared private state for consensus, this obviously works for any kind of POS system. AIs are essentially new L1s, and they have the same problem that any L1 or L2 has in the beginning, which is how do you bootstrap decentralization? You need to have a trusted node network in the beginning, because you're more vulnerable until you actually get liquidity and you actually get use case. So one of the attack vectors that prevents these projects from scaling decentralization and adding to their node validator network is lazy nodes coming in and just copying a lead validator and getting the rewards that are actually doing the computation. So this is a large addressable market, but the AI sweet spot is really powerful. So again, the other kinds of consensus that have to be achieved, this is what we did. This is kind of just an overview of BitTensor, and I think Ashley may have had this slide as well. But we have other, so looking at the, let's go to, yeah, we'll leave this up here because this is a good visual. So you have other projects coming online like Supersite, where you have crypto-specific LLM aggregators. So a user will submit a query to someone like SuperSite. SuperSite then goes to all the different LLMs, finds the one that can service the query best, and then produces that result. Well, the node operator network is deciding which LLM do we go to, or which one gave us the best result, and we want this to happen in a decentralized fashion. So if you create a shared private state, again, you increase the security, you increase the quality of the output. And again, the user experience is now better because the model or that service that they're using through SuperSite is more advanced. Another example that we're seeing in AI that's really popular right now is trying to protect the actual developers making models and allowing them to punch up. So in other words, to make models and to monetize models so that they can stay in the game, continue to make models and iterate. One way to do that is to create a shared private state for the inference. So Magnet AI is one example. Doing this, they have a concept called the ModelFi economy. Another example is Allura. So both of them are interested in finding ways to allow models to miners to make models and protect their inference. So if you've been following ChatGPT 4's product journey, ChatGPT 4.0 used the inference from ChatGPT 4 to build 4.0. So if we can actually keep that on the miner side, allow them to build with the inference that's generated from their models, you allow them to productize, allow them to make more income, and actually stay in the game and punch up above their weight class. So this, broadly speaking, is our framework for FHE validation that Ashley went over as well. And then she did a lot more service to the Zama partnership than I will be able to do here. But ultimately, we believe that if FHE is the holy grail of cryptography, FHE LLMs are probably the holy grail of AI. So to at least go take the first step in that, we're finding that this framework is going to be really powerful. Now, when it comes to actual use cases, like what kind of use cases are these miners going to be building? We see a lot of price prediction right now in crypto AI. That seems to be like the sexy use case. Everyone's trying to like beat the market and get alpha. But there are other use cases like predictive writing. I think agentic workflows are going to be really popular. So we're excited to see this market grow. Right now, the use cases are still kind of basic and maybe more primitive. But this will be an exciting, I think, movement. And so, again, in the effort to find product market fit with FHE, we don't have the luxury of waiting for hardware acceleration. And all of these projects on the left in the consensus security that are using our FHE validation, they all typically have this window of time where validators are coming to consensus. It's 10 to 20 minutes. So even for the most complex FHE computation, we still have time to get it done. In some cases, maybe it takes us like 16 minutes for really complex computation. Ashley will check me if I'm wrong on that. But we still have enough time in that window. So if we can find spots in tech stacks, again, where there's a time window, where there's already consensus that's being derived, and there's a block of time in which to do that, we have time to run FHE. Now, in the data security, these projects are using us for maybe some different applications. So when you go to INET and you try to ask for a cluster, there's a consensus that has to be achieved on where to source the compute from, where it makes the most sense in the world, what's the most energy efficient place to source compute. So that's where we also can create a shared private state for those validators to do their work as well. So we're seeing more use cases, and AI, broadly speaking, is just really ripe right now for in order for it to be able to punch up and kind of compete. And yeah, Ashley went over, I think, some of our credentials, so I won't go too much over this. But that's been part of our journey finding product market fit with FHE. So let me know if you have any questions. Thank you. Yes. Oh, and Ashley just left too.
Yeah, thanks for it's really interesting. So you've mentioned the consensus for the LLM models. So maybe a naive question, like given the language model's response is not deterministic, like the same input will produce this different output, how exactly it's like, what's the standard for tackling this issue? Like it's like obviously like when you have oracles providing deterministic responses, nodes, essentially you can, consensus can decide which answer is the right one. Like how does it solve with language models?
Yeah, it's a good question. That problem is really being solved by SuperSite. So we don't deal with that specifically. We just create the shared private state. Maybe Ashley can speak to that too. But so we don't solve that problem per se. The proof of intelligence framework that Ashley was going over does does kind of use FHE in that regard. But with projects like SuperSite or LLM aggregators, they're dealing with the actual LLM specifically, but they're node operators that pick where to go or the quality of a output. That's where we create a shared private state. Alrighty, thank you everybody. Appreciate you.